Yes, ma'am. Yeah.
Thank you. So let's just get started. So today uh, is our session 4, wherein we have some problem solving uh, based on the content of week 4. So for today's session, let me just brief what were the content of week 4. So the main syllabus covered was on the impedance matching in a transmission line. So I hope you all of you know the significance of impedance matching, wherein to just brief out, say you have a transmission line of characteristic impedance, say Z naught, and some, say, any load ZL. If this Z naught is not matching to ZL, uh, all of us know that there will be reflections, and whenever there is no impedance matching, the maximum power cannot be transferred from this Z naught to ZL. So therefore, we might require something called as a matching network. Matching network. Okay. So the Z naught, the characteristic impedance, is a particular there are typical values for this characteristic impedance, say 50 ohm, 75 ohms, etc. Whereas the load impedances could be anything. So we don't have a freedom of changing Z naught, and we also have multiple loads. It could be anything. It could be a real, the resistance. It could be reactive impedance. So it could be anything. So we need to have a matching network in whenever the Z naught is not equal to ZL. So that is the relevance of ZL. Now, coming to what has been discussed week wise. So, the lecture wise, the first lecture of week 4 had discussions on impedance matching using L section and series stub network. So to brief out what is an L section, so you have something like this: JX, JB. Say this could be called as a L section network, which is a matching network, which is going to match this load ZL to Z naught. Okay. So, so this kind of an L section could be used when real part of ZL is greater than Z naught. So you know what is real part of ZL. Say if this is a reactive, a complex impedance, take the real part of that. If that real part is greater than Z naught, you can use this kind of an LC network. Okay, LC section network. If this real part of ZL is less than Z naught, then you have to use a matching network like this, LC network like this. So this is something which I wanted to brief out. This was already discussed in the video lecture, but this is a very important takeaway from the video lecture the very first video lecture on the L section. So based on the load impedance and the characteristic impedance value, how do you choose the L section network? Okay, so also we had short discussions on series stub, then shunt stub, and a double stub and a quarter wave transformer. So I hope you remember what was a shunt stub. So so say you have a transmission line of characteristic impedance Z0. Suppose you attach something like another transmission line, which is say kind of a short circuited stub or something. It could be anything. This is a short circuited stub which is being attached in shunt to this transmission line. So this is called as a shunt stub. So impedance matching could be done using a series stub, using a shunt stub. It could be a double stub wherein you have two different sections of transmission line connected to the transmission line. Similarly, we have the quarter wave transformer. So I hope you remember the concept of quarter wave transformer also, wherein suppose you have a Z0 and ZL. You have a quarter wave transformer means you have a transmission line of length lambda by 4, which is being connected between Z0 and ZL, okay, whose impedance, so there is a condition for the impedance value of this quarter wave transformer. It should be equal to Z0, square root of Z0 into ZL, okay. Only then we have a matching condition. So this has been discussed in detail, just giving a brief of all these things. Now, the last lecture was on multi-section matching networks and tapered lines. So if you remember, one example of multi-section matching network was the binomial 2-section or 3-section binomial transformers, and tapered lines, if you remember, the exponential tapering, all those kind of transmission lines. So we will have some sample numericals based on these topics. And before I begin, I hope this quarter wave transformer, the idea of quarter wave transformer is clear. So there are two conditions in case of a quarter wave transformer. One is the length of the line should be lambda by 4. And the second condition is the impedance of the quarter wave transformer should be square root of Z0 into ZL. So if you are trying to match ZL to Z0, then it should be like this. Okay. So the idea of quarter wave transformer, let me tell you. So you are attaching a section of another section of a transmission line. So this is basically a section of transmission line. Okay. So when you are inserting this section, it is evident that when you have to do some cancellation. So what is the idea of impedance matching? There will if Z0 is not equal to ZL, there will be reflections. So if you want to avoid that reflection, we need to cancel it. So in terms of interference, if you say you want to cancel the backward waves, okay. So that cancellation will happen. Yeah, yes, right. So if that cancellation, say we know that you have two waves. How does it destructively interfere or constructively interfere? So those kind of ideas you have. So then you know when there should be two conditions. If for two waves, say one wave has to cancel, if the reflections has to cancel, then the amplitudes have to be equal, then the phase difference has to be 180 degree. So these two conditions, when it is satisfied, so this quarter wave transformer acts as an impedance matching network. Okay, so that is something which I wanted to convey. So, and other thing is, about one more thing about the quarter wave transformer. Suppose you have a load ZL and this is Z naught and this length is lambda by 4. Can you tell what is Z in? What is Z in? This is an open question. Please try to. Hello? Yeah,
Root
please.
of Z naught.
Yeah, this question is slightly different.
Z which is root of Z naught is ZL.
Okay, yeah, please tell. Z? Okay, I think I heard you like this. Z naught should be. Yeah, okay. Let me correct you. I am not asking about the Z quarter wave transformer. So we know that the quarter wave transformer equation, that is what you have written. Quarter wave transformers impedance should be, that line's impedance should be square root of Z naught into ZL. Okay. Now, I am telling this quarter wave transformer has a characteristic impedance Z naught. Okay. Now, what is this Z in? This is lambda by 4 length. This is the load. And saying this ZQWT is Z naught. Okay. Can you tell what is Z in? The input impedance looking into that terminals. If you use the same concept, yeah, input impedance cannot be always 50 ohms. So what I am trying to say is, say this is quarter wave transformers impedance ZQWT, that is Z naught, is equal to root of, so this Z naught, so this Z naught is, okay, if you have a load,
Z naught which is equal to.
Yeah, so I am trying to say how much will be the transferred impedance at this point. So that will be Z naught square divided by ZL. Okay. So if you cross multiply and see what is Z naught, square root of Z in into ZL. So this is similar to what equation we have here. So Z in is the transformed impedance. So this concept, is that clear or do you want me to repeat? Okay. So this is what, this concept will be useful to solve the next question. So try to look at this question here. So the very first question here. So you have a transmission line. So you say line 1. Okay. I hope you can see the line 1 has a characteristic impedance Z naught. Okay. Then there is another line, line 2, again with a characteristic impedance Z naught. Okay. And another one more line, line 3 with a characteristic impedance Z naught. Okay. And if you notice, all these lines have a length lambda by 4. Okay. All these lines have a length of lambda by 4. And line 2, there is a termination 200 ohm. And if you look at line 3, the termination is a short circuit. Okay. Now, the question is, okay, consider the transmission line setup shown in the above figure. Find the input impedance looking into line 1. Okay. Can you find this? This is the question. Okay. you have basically three different lines, but all with the same characteristic impedance. From the figure, it is clear how it is being connected. Okay, how it is being connected. You can see. Can you tell how this line 2 is and line 3, are they parallel lines?
Yes, ma'am. Line 2 and line 3 is parallel.
Yes, right. Now, in that case, to solve this, can we just look at this and this impedances? Okay, let me write, because this is line 2, I will write it like Z in looking into line 2, and this is Z in looking into line 3. Okay, because they are parallel, I can tell at this point, okay, at this point, the impedance will be Z in 2 parallel Z in 3. Okay. Now,
Yes, ma'am.
can you find what is Z in 2? So remember, you have a length of lambda by 4. So there is a quarter wave transformer whose load value is 200. So what will be the transformed impedance Z in 2? Use
Z
this.
into is equal to Z
Use
naught square upon
ZL.
200.
Yes, exactly. So Z naught square by 200. Similarly, what is Z in 3? Use the same logic. The only thing is you have a short. So what is Z in 3? The impedance looking from line 3, looking into line 3.
0.
Yes, Z naught square by ZL. Here, because it is a short circuit, this becomes 0 and I can say it is infinity. Now, what is Z in 2 parallel to Z in 3? An
Z naught
impedance
square upon
parallel
200.
to infinity. Yeah, definitely. So, I can write Z in 2 parallel Z in 3 is Z naught square by 200. Now, this line is going to reduce like this. So, this is my line 1 with the characteristic impedance Z naught. And at the end of this line, you have Z naught square by 200. Okay. And this length is lambda by 4. Now tell me what is Z in. The same logic applies. Logic for lambda by 4 line.
200, ma'am.
Yes. So Z naught square by 200 divided by Z naught square by Z naught square by 200. This becomes 200 ohm. So I hope this question is clear.
Okay.
Okay. Hope this is clear. We'll move to the next question.
Yes, ma'am.
Yeah. I think this you can attempt on your own. This is a very simple question. Please attempt and uh, give your answers in the chat. A lossless quarter wave transformer is used to match a 50 ohm load to a 100 ohm line. So this will be square root of Z0 into ZL, which is 100 into 50. I think there are some answers in the chat. 25 ohm. 200 ohm. There are two options. I think it's a simple question. Please. I hope everybody is able to solve this. So the right answer is 70.71. So let's move to the next question. Yeah. Yes, that's the right answer. 70.7. Okay. Now let's move to the next question. So I hope the question is clear. So which of the following configurations of lumped elements with appropriate component values can be used to match a load impedance of 100 ohm to a transmission line of characteristic impedance 50 ohm at a given frequency of operation? So you know what is the characteristic impedance and what is the load impedance. Can you tell which of these L section networks could be used to do the matching? I think this is based on the very first statement which I made about the LC network. If you remember clearly, based on these conditions, we decide what kind of LC network could be used. So, can you please attempt this question based on that idea? Which of these configurations could be used? Given condition, I will write it down. ZL is 100 ohm and Z0 is 50 ohm. Based on this knowledge, can you tell which L section network can be used? Or which of these configurations? Can you use all these configurations? This is an open question. Write in the chat if what do you think. Or you can even unmute yourself and answer. So I would like to...
Option A.
Okay, option A. Is there any other option also? Or is
No,
it
ma'am.
just option A?
मैम फोर्थ ऑप्शन दिख नहीं रहा है.
Okay, you can't see here. So in fourth option, you have a parallel L and series C.
First and second option.
Okay. So tell me why. What is the reason for the choice of first and second? I mean, option A
Because
and option B.
RL is greater than 2 characteristic impedance.
Yes. So RL is greater than RC here. Okay. So that's the reason we choose either. So in general, we can say it should be JX, JB. Okay, this should be the L section network to be used. So it could be CL or it could be LC. So these are the two options. So option A and B are possible options. So I hope this is clear. We'll move to the next. So now we have a question again on the L section impedance matching network. Okay, so try to look at this question. L section matching network shown below is used to match a 100 ohm load to a 50 ohm line at 500 megahertz. So if you notice here, again the same condition, RL is greater than RC. Okay, or I can write ZL is greater than Z0 here. So the network to be used should be what? JX, JB. Okay, so this is ZL and this is Z. Now, so the frequency is given, value of inductance is given. You need to find the value of capacitance. That is the question. Is there any standard formulas which you have come across during the video lectures? Can you remember that? In case of an L section network, I hope you remember this. B is equal to XL.
Ma'am, B is equal to
Yeah.
plus minus under root Z0 minus RL upon RL
Yeah.
upon Z0.
Okay. So if you have gone through the lectures, you know this. And from B, you can find what? C. It will be B by 2 pi F. So this is the capacitance. So XL and RL, it's clear. It is based on ZL. So wherein I can write ZL is nothing but RL plus JXL. So here what is the value of XL? In this problem.
Zero.
Yeah, XL is 0. So your expression for B reduces to plus minus square root of 100 by 50 into root of 100 square plus minus 100 into 50 divided by RL square 100 square. So what will be the value of B? Can you please try to solve this? What will be the value of B? So you should be getting plus minus 1 by 100. So from that C you can find out B by 2 pi F plus minus 1 by 100. Yeah, right. It's the right answer. 1 by 100 divided. So can you find C now? 2 pi into F, you have to use 500 megahertz. 500 into 10 power 6. Can you try finding the final answer? And you can notice that the answers are in terms of pi. So you need not reduce that. So just look at the expression and it's in picofarad. So maybe you can just omit this plus minus. It's not needed.
Ten by pi.
Yeah, right answer. So you have the final answer 10 by pi picofarad. Okay. So if you know this L section network, how to find out the C, if you know the formula and if you know the load value, that is the RL plus JXL and the Z0, you can calculate B. From B, you can find out C. Okay. So let's move to the next question. If there are any doubts, please ask. I think it's very clear. Okay, so let's see how do we do this one. So this is a slightly different question. If you notice, here you have your RL less than Z0 or ZL less than Z0. And look at the kind of matching network used. So you have parallel this JB and then JX. And this is ZL and Z0. Okay. Now, operating frequency is again given to you. Now, how do you calculate L and C for this? Here you need to find both L and C. So let me give you the equations. I hope you would have gone through the lecture videos. There you would have come across this. ZL by 2 pi F and C is 1 by 2 pi F Z0. Please try to find out this L and C values. Substitute for ZL and F and Z0. ZL is 25 by 2 pi, F is 500. Answers are in nanohenry for inductance and picofarad for capacitor.
Option A.
Okay. So here if you solve, yes, you will definitely get it as 25 by pi. As you can see here, it becomes nanohenry. And here you will get 20 by pi picofarad. So I think the L section network and how to find the inductance and capacitance is clear. So now let's move to another question. A load impedance is to be matched to a lossless transmission line of characteristic impedance 40 ohm using a length of a lossless transmission line of characteristic impedance Z1. Okay. So here, as per the question, you have a characteristic impedance Z0 as 40 ohm, and then you have a section of transmission line having a characteristic impedance Z1, which is trying to match the load. Okay, so this load is 50 plus J10. The question is, what is Z1? What is Z1? Any idea how do we find this? You can give your suggestion. So all of us know the purpose of Z1. Z1 is trying to match. So Z1 is trying to match this at this place to ZL and at here to Z0. So that is the purpose of Z1. Okay, so you will tend to see that option is to take square root of 40 and 50 plus J10. But have you noticed that it is not mentioned that we to use a quarter wave transformer? So there is, it's not a question of quarter wave transformer. So then how do we solve it?
Is it not?
Yeah, please go ahead. Okay, I think somebody was trying to talk. I think I couldn't hear. Okay, so let me give you some clues onto this. So if you look at this particular network, can you think at this point, can you try to find out the Zin, that is the input impedance. So input impedance is Zin is equal to Z1 into ZL plus J Z1 tan beta L divided by Z1 plus J ZL tan beta L. So if you remember the expression for input impedance in case of when we discuss the transmission lines, I hope you remember in case of a lossless transmission line, you had this expression. So I have used that same expression to write here. So when I write here, I am taking Z1 as the characteristic impedance and beta L as the length of the transmission, the electrical length of the transmission line. Then ZL is the load. Okay. So based on that, I can write the expression for Zin. Now, this Zin has to be 40 ohms. Okay. Here, based on this network, I can say that this Zin has to be 40. That means that Zin, this was a complex impedance which needs to be transformed to a real impedance with the help of this particular section. For simplification purpose, let's take this tan beta L assume it is like t. Okay, let it be assume it as t. So because for a particular constant length of the transmission line, tan beta L is t. Tan beta L is a constant number. Okay, so to use this, what we have to do is, so as I told, Zin is 40. So that is equal to Z1 into ZL plus JZ1. So ZL is, here it is 50 plus J10. Okay, plus JZ1. So Z1 is the unknown here. We are trying to find out that Z1. Okay, and let me put this tan beta L for simplicity. I am putting it as just T. Okay, divided by Z1. So what is Z1? We do not know. Plus JZL. 50 plus J10. Again multiplied by tan beta L. So I'll put it as T. Okay. Now cross multiplying this, I can write, I can simplify this. Z1 into 50 plus J is common, so J I am taking it out, J into 10 plus Z1 T is equal to 40 Z1 plus 40 into J50 minus 10 T. Okay. So,
Madam, J50T it will come now. The T is common.
you are talking about which side?
40 is it that right side, madam.
Okay, 40 Z1
Is it
plus
plus 40
40 J50.
T.
Okay. Yes. Thank you. Okay, J50T minus 10T. Now suppose, so this is an expression. If you try to equate the real parts, equate the real part. Can you try equating? On the left hand side, you will have 50 Z1. Anything else? No. On the right hand side, what you have? 40 Z1. And what else we have as real? Minus 400. So 40 into 10 minus 400T. Now simplifying this, you will get 10Z1 is equal to minus 400T, or I can write Z1 is equal to minus 40T. So this is one of the equation. Okay. So similarly, can you equate the imaginary part? Okay. So if you equate the imaginary part, what you will get? Equating imaginary parts, what you are going to get will be Z1 into, here imaginary parts you have 10 plus Z1T. Okay. 10 plus Z1T. I am taking the J terms is equal to, on the other side we have, if you see 40 into 50, that is 2000 T. Okay, 2000 T. So that is my imaginary part on the right hand side. So this simplifies to, so suppose if I substitute for z1, this will simplify and you will be able to solve this. So using these two equations, you can solve for the value of t. Can you try? Putting z1 is equal to minus 40t into the second equation, you can solve for the value of t. So it will be a cubic root, a t cube. T cube equation is of the form of t cube plus so and so t. So there will be 3 solutions because it is a t cube. There will be 3 solutions, and this what do we have to do is substitute for this z1 here. Z1 has to be put as minus 40t and solve for the t. Hello? Yeah, 2.25. So I think there is a small mistake somewhere in the solution for D. So you can recheck. So you must be getting t value as plus or minus root 3 by 2, and or it could be 0 also. So there are 3 solutions because it has t cube. It should have 3 solutions. If you want, I will just write down the equation also. So Z1 is minus 40t. So it will be minus 400t plus Z1 square. So Z1 square will be Z1 square into t will be 1600 t square. So t cube, okay, is equal to 2000 t. Yeah, yes. I am seeing in chat. What is your equation? Minus 400 t, 16 t cube, 1600 t cube is equal to 2000 t. Okay. So once you solve this, you will be able to get this t value. So it is a cubic root. So in calculator, just put in. So how to solve? What you can do is in calculator, you take the equation with the power 3 and substitute the coefficients for t cube, t square it is 0, and for t it will be minus 2400. So then you will get the answer for t.
Hello, madam.
Hello, please tell.
Madam, that equations, I went to that mode. That equations, unknown values 2 or 3, madam.
No. It's not unknown value. See, try to take the t. Say, how do we solve x square quadratic equation? You use the equation mode, right? With the power 2. So then it will ask. Say, I'll write down here. Say, for example, if it is ax square plus bx plus c is equal to 0, what we choose is equation power 2. Then it will ask for a, b and c. Right?
Okay, madam.
In that you have to substitute the values for a, b and c. Similarly, here we have the t cube. So if I write it again, it should be 1600 t cube minus 2400 t is equal to 0. Okay. So t will have, so basically what you have to do, in the t cube coefficient you have to write 1600. T square, there is no coefficient, put it as 0. In t you put the coefficient as minus 2400. Then the constant term is 0. Then you will be able to solve for the value of t.
A is 1600, B value is 0, is 240.
Minus 2400, please.
Madam, I put that x zone, it is coming 1.2, like that is coming. Madam, that equation mode we have to select degree is 3, no?
Degree is 3, correct?
3 I selected, madam.
So what are the inputs?
They are asking A value is 1600.
Yes.
B value 0.
Yes.
C value minus 2400.
Yes.
D value constant 0. Then I get the x1 which is equal to 1.2247. It is coming.
1.2247. Okay. What is the other value? X2?
X2 0. X3 minus 1.2247. Exactly.
So you
Correct,
have,
madam?
yes, you have 3 solutions, right?
1.2247.
Okay.
0 minus 1.2247.
Yes, that is right answer. So now we haven't reached to the answer. So what is to be found? Question is to find the
49.
Z1. So what
49
do we do? So now you see it cannot be 0, and also it cannot, so there are 3 solutions out of which you cannot choose the 2 solutions. 0 is not possible, plus root 3 by 2 is also not possible. Why? Because Z1 is minus 40t. Okay. So it will be minus 40 into minus root 3 by 2, or whatever you got it as 1.2247. So if you multiply that, you will get it as 48.988, which is almost close to 49. Is that clear now?
Yes, ma'am.
Okay.
Ma'am, when
yes,
create imaginary part, then in that equation, put the value of t in terms of z. then there is no problem to solve this question. Very easy.
Okay. Please tell once again.
Ma'am, when we equate the imaginary part,
Yes,
then
exactly.
in that equation,
Ah.
in terms of Z1 and T,
Ah.
but put the value of T from first equation, from real part.
Yes. That is the
Then
other
there is
way
no
to
problem.
solve
Very
it.
easy.
So it is like it will be in terms of Z1, directly in terms of Z1.
Yes, ma'am. There is
Correct.
no need to solve the cube root equation.
Okay. That is a good suggestion. Thank you. Yeah, I hope you got it clear. So what he was saying is, instead of substituting for Z1, substitute for T. Substitute for T value as Z1 by 40. So then it becomes much more simple. No need to go for the solution in the other way around.
Cube equation.
Cube equation. Okay, you can try that out. Thank you for the suggestion, Amit. Okay. So I think this we can go ahead. Okay, let's go to problem 7. So this question is from binomial transformer, which is a 2-section transformer. So if you remember in the beginning, I have discussed about the last video lecture was on multi-section matching network, wherein one of them is called as the binomial transformer, which is basically here having 2 sections. So n is equal to 2. This is used to match a 150 ohm load to a 50 ohm line. So the question is, what is the characteristic impedance of the 2 sections? So the section 1, section 2, there are 2 sections required to match 150 ohm to 50 ohm. Okay. So what is the impedance of these 2 sections required? Okay. So to solve this, you should know the formula for the binomial transformer. So I hope you remember this formula. Okay. So wherein the capital N is the number of sections and the small n is the section 1, section 2. So if you want to find the impedance of the section 1, what you do is n is equal to 0. Put n is equal to 0 if you want to find the impedance of section 1. Okay. For that, what you will get? Z1 by Z0 is equal to 2 power minus 2. Sorry, this is Cn. Okay, small letter. So C0 raised to minus 2. Ln of ZL is 150 and Z0 is 50. Okay. So you have to try to picturize this. So this is something like section 2 and this another section 1. And then this is your load and this is your characteristic impedance. So section 1 will transform ZL to something and then section 2 will transform that to Z0. That's the idea here. Okay. So from this expression, you know the value of Z0, you can substitute here. And if you notice, there is something called a C0, C1, that coefficients. So if you go through the video lectures, you will see that there is a table wherein you will have the values of C0, C1, etc. So from that table, you can pick up the value of C0, C1 and then take the raised to minus 2. That's all. Okay. Then you will be able to solve for what? Z1. Okay. Now coming to section 2, what you do is put n is equal to 1. So ln of Z2 by Z1 is equal to 2 raised to minus 2, C1 raised to minus 2, ln of 150 by 50. So from this, you can find out what is Z2. So whatever Z1 you have got here, you have to substitute it here. Then you can find out what is Z2. Is this clear? Any doubts?
For both section, ZL is 150.
Oh, sorry. I have to make this change. Just a minute. Yeah, both the sections ZL is 150. The only thing is you have to replace Z1 and Z2 in the left hand side.
Okay, ma'am.
So we are trying to make what? ZL to Z1, then from Z1 to Z2 with a section. So it is like consequent sections. So with section 1, the impedance is transformed to Z1. From the with the help of section 2, it is being transformed to Z2. There are 2 sections. Which will eventually make ZL match to Z0.
Okay, ma'am.
Okay. So let's go to the last question here. So this question is on an exponential taper section. This is designed for matching a 100 ohm load. You have a 100 ohm load, which is ZL, and 50 ohm line, Z0. Okay. So you have a taper section. Okay. There is a taper section. So it means like an exponential taper section. So I hope you understand what is an exponential taper section. It's like a line which has varying length, varying width. So the length of that line is given as lambda by 2. So that taper section is matched, is designed such that it will match 100 ohm to 50 ohm. So I hope you remember the considering this equation for a taper section. So the reflection coefficient is half ln of ZL by Z naught e raised to minus j beta L sin beta L by beta L. Okay. So we know the value of ZL as 100, Z naught as 50. Okay. And beta L is 2 pi by lambda into lambda by 2. So this will become pi. So sin beta L will become 0. So what will be the reflection coefficient? That will be 0. So the question is on the magnitude of reflection coefficient, although the expression is having the magnitude as well as the phase. So we are considering only the magnitude part.
Ma'am, please one more time repeat.
Okay, so again, this is exponential taper section is a particular matching network like any L section network or a multi-section network. This is just a section of transmission line, but the difference is the dimension of the section is like exponentially tapered section. Okay, but the length is constant. So the length is like lambda by 2. So depending on the length of any line, you know that say any line length, say any impedance, you know the expression for Zin. Depending on the length beta L, any impedance will be transformed to this Zin, particular transmission, particular impedance. So similar to that, this has a transmission line length of lambda by 2. So with that length, what is the what has to happen? This has to match to 50 ohm. So this will ensure that it will match. So if the length of this line is lambda by 2, the question is what is the magnitude of reflection coefficient? So this is the expression for the reflection coefficient. As you can see, this has the magnitude part, and if you notice this e raised to minus j beta L, that is the phase part of the reflection coefficient. Okay. So the question is on magnitude of the reflection coefficient. So you can notice that the gamma is directly proportional to sin beta L. So whenever sin beta L goes to 0, that means whenever beta L becomes m pi, in that case, the magnitude of the reflection coefficient will become 0. So that is something to notice here. So the length of the line is very important. Depending on the line, the reflections will have a change. So in this particular case, the length is such that the reflection becomes, the reflection coefficient becomes 0. Is that clear?
Yes, ma'am.
Okay. So now the session is open for any questions of last week or previous week assignments, or we'll try to discuss if you have any doubts. I think I had a question from Arun Raj. I'll go through it. So meanwhile, if you have any questions, you can let me know.
Ma'am,
Yeah. Huh.
there is a question in which length of the transmission line is lambda by 8
Okay.
and load is complex.
Mm.
And for the matching of this, there is a impedance jx connected series.
Okay. Series or how it is connected? Are you discussing some question from assignment?
Yes, yes.
Okay.
Assignment 4, question number 3.
Just a moment. Okay, please. So we are not supposed to discuss assignment questions. So, what is your doubt?
Ma'am, I think I will use the general equation of input impedance Zn is equal to Z0 ZL
Okay.
plus Z.
Okay. So try to understand. I hope you understood the question. So the issue is you have a load impedance. Okay.
Yes.
Then you have a series connected some unknown impedance.
Yes.
And there is a length of the transmission line like lambda by 8.
Given. Yes.
Okay.
Yes.
So it is the simple question of transforming the impedance.
Okay.
Okay. So it is told like Zin equal to Z0 value of X's. If you want to say that Zin is Z0. So ultimately you find out Zin, equate it to Z0, use the transformation equation of Zin.
Okay.
Take considering the length of the line, you can find it out. Okay.
Okay.
That much clue I can give you. Okay.
Yes. Okay.
Any other doubts in the previous assignment or something?
Hello.
Hello.
Ma'am,
Yes, please.
in last question,
Mm.
in taper section,
Mm.
if the question is find the magnitude of reflection coefficient,
Mm.
then in that formula, we will ignore exponential term.
Yes, yes.
Okay.
So phase term, basically the phase term.
Yes, yes. Okay.
Madam,
Yes.
madam, you have microwave David Boser PDF file, madam. PDF book.
Which book?
Microwave engineering,
Oh,
Boser.
okay. D for sir. I'm
In
not
my
sh-
college, it is not available, madam. That's what I
I
need PDF file.
Okay, let me check and get back to you. If I have, I'll share with you in your
Uh,
email ID from where you have
okay,
sent it.
madam.
I'm not sure if I have. I have to check back. Mostly, I need to check. Okay.
Okay, madam.
Hello. Arun Raj is there? Okay. So I was
Yes,
going
ma'am.
through that question which you have sent. Uh, so your answer is correct, right?
Yes, ma'am. One more person also they told on that day 0.28 gigahertz.
Okay. So I
That-
think I have mentioned the answer as 0.28 gigahertz, right?
but you told 28.5
No.
gigahertz,
Not
madam.
28. I was just going through the actually the original lecture because I also got doubt whether I told like that. Uh, because I was just going through the video recording. I think I mentioned as 0.28. Uh, okay. Okay, so I think maybe I made a mistake somewhere. So I think the right answer is 0.28 gigahertz only. If there is any corrections, I will send you a detailed answer. But right now, whatever I am seeing, it's 0.28 gigahertz. But I will still try to solve it once again. And if there is any corrections, I will let you know. Yeah, I verified that answer once again. So it is 0.285 gigahertz. If I have if I have mentioned like 28.5, please uh, excuse me, like it is 0.285 gigahertz. Okay. Hello. Okay, I hope you are.
Okay, thank you, madam.
Okay,
Thank you,
okay.
madam.
I verified it. I think by mistake I might have mentioned that. Okay. If there are any other doubts, please ask or we'll wind up the session for today. Can we wind up?
Yes, ma'am.
Okay, okay. Then we'll meet next week.
Okay.
Thank you.
Thank you,
Bye.
ma'am. Thank you, ma'am.